Hi everyone, I'm Hwei-Shin Harriman, an undergraduate at Olin College of Engineering, and today I'll be introducing Edgeworth, a tool for authoring diagrammatic problems. Solving diagrammatic problems builds connections between mathematical expressions and visual representations, which is known to increase conceptual understanding and flexibility. Despite the known benefits, mathematical teaching materials often suffer from too few diagrams. We interviewed content authors and found that authoring such problems remains a tedious manual process. Even creating simple shapes can be challenging, so problem authors often resort to recycling course content, providing multiple similar examples, or repurposing diagrams found online. And the challenges compound when considering the issue of scale, as many existing tools lack support for high-level tweaking of diagrams or are difficult to use for non-programmers. To demonstrate how Edgeworth addresses these challenges, let's look at an example. Let's say this math teacher is leading a geometry lesson and wants to teach their students about the triangle congruency theorem. As a quick reminder, the theorem states that two triangles are congruent when they are the same shape and size. The teacher forms a mathematical question, for example, in which of the following diagrams are triangles CED and AED congruent? Then they ask the student to choose diagrams that correctly answer the question from a list of possible options. In a multiple choice format, the problem might look something like this. But our teacher doesn't have enough time to make all of these diagrams from scratch. Thankfully, there is a way to generate these diagrams with just a few programmatic statements. Using a tool that we developed in prior work called Penrose, we have the capability to define a programmatic encoding of a given problem's mathematical notation and generate diagrams with a one-to-one representation, such as this snippet, which defines the content in the upper left diagram. Because of the direct relationship between the body of the code and the rendered diagram in Penrose, it follows that if we make changes to the program, it will change the resulting diagram. So even subtle changes in code will result in diagrams that correspond to slightly different math. For the specific use case of creating answers to multiple choice questions, there are a few different types of answers that we encounter. Beyond the obviously correct and incorrect answers, there are also what we call distractors, which are answers that appear correct but aren't, and correct special cases, which are diagrams that show a valid alternate representation of the answer in a different or less obvious way than the standard position. To reduce the overhead of creating dozens of unique diagrams per problem, we want to generate all of these answer types using only a small amount of input from the problem author. We can accomplish this goal in Edgeworth by making use of program mutation techniques. Program mutation refers to the technique of programmatically altering the content of a program. These alterations are typically made using what are called mutators, which are predefined permutations that can be made on the original program and often vary between use cases and languages. Program mutation is often encountered in mutation testing and program repair. These applications use program mutation to make syntactic changes to a source program to improve test suite coverage and uncover hard-to-find bugs. Using Penrose's one-to-one correspondence between mathematical notation and diagrams, Edgeworth uses program mutation to automatically generate dozens of related diagrams by slightly altering the author's programmatic encoding. We are specifically interested in the pathways that are very close to the source program. This is because, when generating answers to a multiple choice question, we care specifically about diagrams that are mathematically similar to each other. If the diagrams are too different, the problem loses its value. Using this line of thought, we uncovered three types of mutation operators through our exploration of geometry problems: adds, deletes, and edits. There are currently 4 edit operations, which mutate various portions of a statement, such as the return type in type change or the ordering of parameters in swap arguments. This set of operators is not necessarily exhaustive, but we found they provided sufficient coverage and flexibility for our chosen domain of high school geometry. I will speak more to how we developed these mutators in the analysis portion. Now, let's return to our example question and look at each of those diagrams in detail. In which of the following diagrams are triangles CED and AED congruent? Here is an example of the standard position that corresponds to this problem, defined by the author's input. The two triangles are congruent due to the side-angle-side congruency theorem. So you can see that we've defined 5 points, and then we said that we want 4 triangles to be made up by those 5 points. And we said that we want points B, E, and D to be in the same line, so they're collinear. And we say we want the interior angle CEB to be a right angle. And lastly, we say that we want the line segments CE and EA to be the same length. So, given our set of operators, what alterations to this source program could we make to result in at least one of each of our answer categories? We could remove a couple of statements, in this case resulting in a random incorrect answer, where the two triangles are clearly no longer congruent. Or we could add additional constraints, in this case forcing angle BEA to be less than 90 degrees. This results in a distractor. Both angles appear to be nearly the same size, but they are no longer congruent because their angles are not equivalent. Or we could replace the arguments in equal length marked with two other line segments, in this case resulting in a correct special case where the two triangles are still congruent due to the right hypotenuse leg congruency theorem. Edgeworth's functionality is packaged into a web authoring interface written in React, so let's take a quick look at what it looks like from a user's perspective. To begin, users authored their source program in the upper left text box. The domain and style sections are provided for advanced Edgeworth users. They're used by Edgeworth to define the domain of statements and the visual appearance of diagrams. The sliders adjust the number of diagrams to generate per trial and the number of mutations per diagram. The drop-downs allow the user to select statements that they are interested in having mutated. There's a category for each type of mutation that can occur: adds, edits, and deletes. Edgeworth can only mutate a statement if it is included in at least one of these drop-downs. Edgeworth generates a set of diagrams when the Generate button is pressed. The first diagram is always the source program, while the other diagrams have been mutated randomly within the bounds defined in the configuration. Clicking on a diagram lists specific mutations that were applied and the full mutated program. Clicking Resample adjusts the layout but not the content of the diagram. To select a diagram to export, click on the checkbox. Clicking Export will download all selected diagrams as SVGs onto the user's computer. To evaluate Edgeworth, there were two major questions that we wanted to answer. The first is, are our mutation operators expressive enough to cover problems in a given domain of math? So to answer this question, we worked our way through a popular high school geometry textbook and examined all 53 diagrammatic problems that were found in the chapter review sections. Of the 53, we determined that 24 of those original diagrams visualized distinct concepts, such as parallel lines, different types of polygons, angles, etc. For each question, we reframed it in a way so that the original diagram would be considered a correct answer. Then we identified special cases and distractors and determined the series of mutations required to achieve them, just like we did in the example. This process was also used to develop our final set of mutation operators. If multiple cases required a mutation we had not yet defined, it was added to our set. As a result, for each of the 24 diagrams, we found that it is possible to mutate the source program into at least 3 special cases or distractors using some combination of our 7 mutation operators. Finally, we recreated all 24 of the diagrams from the textbook in Penrose. You can see that we have defined relationships for polygons, circles, triangles, angles, segments, lines, and rays, including the ability to define labeled segments and angles with tick marks as our standard in the Euclidean geometry domain. These became our source programs for the next portion of our analysis, which was answering the question, how often do the diagrams we actually want appear in the programs we generate with Edgeworth? Using Edgeworth, we generated batches of 20 diagrams for several of the 24 source problems. Edgeworth was allowed to make 1 to 3 random mutations per mutated program. Based on multiple trials per problem, we found that Edgeworth easily generates at least 1 correct and incorrect answer in less than 5 mutant programs. We were also able to generate 1 to 2 correct special cases and 1 to 5 distractors per trial, but it is important to note that in order to get these results, we had to be intentional about the statements of interest that we selected. There are several avenues for future work on Edgeworth. For example, currently mutations are randomly selected from our subset for each trial. Part of our ongoing work involves saving mutations that a problem author identifies as good. Maybe this series of mutations resulted in a compelling special case or something, and applying them to other problems. This will improve Edgeworth's ability to generate families of similar problems. In a world with e-learning on the rise, being able to quickly generate dozens of related diagrams can allow educators to regularly update and tailor their learning materials, give additional practice to students who need it, and even combat cheating by giving each student their own unique test content. Thank you.